now seen the notion of continuity of functions in two variables, and now it is time that we talk about limits of functions in two variables. So here first in order to define limits of functions, I need to understand what is a limit point of a set. So let us begin. So suppose that D is a subset of R2, and you can take a point x0 y0 in R2. So here note that I am not saying that x0 y0 is a point in D. So I'll come to why I am saying so. So a point x0 y0 in R2 is said to be a limit point of D if any neighborhood of x0 y0 contains a point of D. Now this is very important, then that this point has to be a point which is not equal to x0 y0. So again, a point x0 y0 in R2 is said to be a limit point of D if any neighborhood of x0 y0 contains a point of D other than x0 y0. So I have said that a limit point need not be a point in the set. So let us draw some pictures in order to understand these things correctly. So suppose I have D to be exactly B of x0 y0 comma r. So what is the description of this set? This contains all the points xy in R2 such that the norm of xy minus x0 y0 is less than r. Okay, so let me draw this. So I'm drawing this circle somewhat vaguely. So this is a point x0 y0. This is a circle of radius r. So what is this B of x0 y0 comma r? This contains all the point which lies inside the circle but not on the boundary of the circle. So this is what D is. So D is everything that lies inside this circle. So you pick up any point inside the circle, and you can see that if you take any neighborhood of this point, this must have a point of the circle which is not equal to the point that we started with. Now what about this point? This point which lies on the boundary of the circle. You can see that if you take any neighborhood in R2, there must exist a point which is not equal to the point which I have started with x0 y0, but this point is common to both D and the neighborhood that you have taken. So this point is a limit point, and of course any point in the circle that I have taken is also a limit point. So let me now go forward. So just one more thing that I want to mention here is that the condition is as follows. So you take any neighborhood. So D is a subset of R2. A point x0 y0 is a limit point if any neighborhood of x0 y0 has a point xy in common to both D and the neighborhood that you have considered, and also the condition is that xy is not equal to x0 y0. So suppose I have a D which somehow looks like this, and I have this point somewhere here. It can be a point on the boundary, it has to be a limit point. Suppose I have picked up a limit point. So now I consider this open disks x0 y0 comma 1 by n, where n varies inside n. So now this is a neighborhood of the point x0 y0 that we have chosen, and if I call this neighborhood, let's say un, so we have seen that un intersection D has a point, let's say xn yn. So xn yn belongs to this intersection, but xn yn is not equal to x0 y0. Now since I have taken this open disk to be of radius 1 by n, you can easily check that this sequence that you will just produce by varying this argument over all n as n varies in natural numbers in the set of natural numbers, this xn yn converges to x0 y0. So what is a way of seeing that? So norm of xn yn minus x0 y0. So this is less than 1 by n. So in particular, xn minus x0 modulus of that is less than 1 by n, and yn minus y0 is less than 1 by n. You can see that this converges to 0, this converges to 0. These are bigger than or equal to 0 because we are talking about modulus, which are always non-negative. So you can see that xn converges to x0, yn converges to y0. So this is going to be very useful when we talk about limits of functions. So let us now forget about the discussion that we have just done and proceed to the definition of limits. So suppose that I have taken D to be a subset of R2. This will be fixed in whatever we are going to talk about during this video. So suppose that I have chosen x0, y0, a limit point of the set D of R2 that we have chosen, and suppose that f is a function from D to R. So note that again x0, y0 may not be a point of D. So as such, f may not be defined at this point x0, y0, but still we can talk about limits. So x0, y0 is a limit point of D, and f is a function from D to R, a real valued function on D. We say that the limit xy tending to x0, y0 of f of xy exists if there exists an L in R such that whenever xn, yn the sequence converges to x0, y0, f of x and yn converges to L. But here is a big condition that I have just mentioned in our discussion that we have made on the right hand side here. So here the condition is that x and yn has to be not equal to x0, y0 for all n. So by what I have just said, if you have chosen x0, y0 to be a limit point, such a sequence always exists. So what is the definition? If you pick up a sequence, if you pick up any sequence that has this property that none of the terms are same as x0, y0, and this sequence converges to x0, y0, then f of x and yn must converge to L as n tends to infinity. So in this case, we say that the limit exists and is equal to L. Let us look at a few examples. So first example is f of xy is equal to sine of xy. So the question is, does this limit as xy tends to 0, 0 f of xy exist? So okay, we have to choose a sequence x and yn converging to 0, 0, but our condition is that xn yn is not equal to 0, 0 for all n. So anyway, that will not matter too much over here. So xn, so by definition of convergence of sequences of two tuples, xn converges to 0, yn converges to 0. So everything happens as n tends to infinity, so I do not mention it here. Now we know that if we have two real sequences xn and yn both converges to 0, then the product of them converges to 0, and we know that the function fx equal to sine x, this real valued function, is continuous on R. So x and yn converges to 0 implies that sine of x and yn converges to 0. So what is the upshot? The upshot is that this limit exists, and not only that, this limit is exactly equal to 0. Then we come to our favorite kind of functions that we have studied, that we have seen when we talked about continuity. So let's say f of xy is xy divided by x square plus y square for xy not equal to 0, 0. Note that here D is not the whole of R2, it is R2 minus 0, 0. Okay, so my question is, does limit xy going to 0 0 f of xy exist? So does this limit exist like in the previous example? Well, let us see. So suppose that to in order to check what is if this function has a limit as xy tends to 0 0, I need to check that for every sequence x and y n in D with x and y n not equal to x0 y0, and in this case this is just 0 comma 0. uh, so x and y n converging to 0 0 must imply that f of x and y n converges to L. Okay, so suppose I take a sequence 1 by n 1 by n, this converges to 0 0. If I plug in every information here, we can see that f of 1 by n 1 by n converges to half. But on the other hand, if I take this sequence 1 by n comma minus 1 by n, then we will see that f of 1 by n comma minus 1 by n converges to minus half. But in order for this limit to hold, we must have that this L should work for all possible sequences x and y n satisfying the necessary conditions. So here I have produced two sequences such that f of 1 by n goes to one value of L, let me call it L1, and f of 1 by n comma minus 1 by n, this converges to another number, let's say L2, and also L1 is not equal to L2. So that violates our conditions for limit, and in this case we say that the limit does not exist. Limit does not exist. So this is our conclusion. Let's go ahead. So now we talk about interior points. So why do we need to do that? We have seen that when we are studying calculus, the words limit and continuity are almost pronounced in the same breath, but that implies that there should be a strong bonding between these two notions, limits and continuity. So here in this slide, let us try to explore the connection between these two notions. So first, suppose that x0 y0 is a point in R2. So it is said to be an interior point of a set of a subset D. So what is an interior point? Okay, so an interior point is as follows. So x0 y0 in D is said to be an interior point if there exists a open disk uh, which is around that point, which is contained inside D. So again, if I take one of our favorite examples, so suppose that I am taking D to be something like that, a small circle with not containing the points on the boundary. I take any point, I can always produce an open neighborhood which is again a circle without without the without the perimeter, so to speak. So every point inside this circle is contained inside this open set, this set D. So this kind of points are called interior points. So what is an interior point again? So a point x0 y0, this must belong to D. So this point is called an interior point if there exists r bigger than 0 such that B x0 y0 comma r is a subset of D. So as such, interior point is a limit point because it is very clear. So if you take this definition, that so let me try to be a little bit more precise. So in order to show that, what do we do? Suppose that x0 y0 is an interior point of D. So then there must exist an r bigger than 0 such that b of x0 y0 comma r is contained inside D. Right, but if you take any neighborhood, if you take any neighborhood of this point, this must intersect this at a point which is not equal to x0 y0. So this implies that an interior point is always a limit point, but the converse is not true. So as we have seen before, that a limit point may not be a point to start with in the subset that we are considering, but an interior point is always contained inside the subset that we are talking about. Okay, so suppose we take x0 y0 to be an interior point of D, and suppose that f is a function, be a function. So f from D to R be a function. So it turns out that f is continuous at x0 y0 if and only if the limit of the function f of xy as xy tends to x0 y0 is equal to f of x0 y0. So to summarize, if we are talking about an interior point, for a function to be continuous, we must have that this limit should exist, and not only that, this has to be equal to f of x0 y0. So what happens if we take a limit point which is not necessarily an interior point? I leave it for you to think about it, and we will discuss during one of our discussion sessions. So I hope this clarifies the relationship between limit and continuity. So let us go forward. So there are some limit theorems which is very easy consequences for limit theorems, consequences of limit theorems for sequences. So suppose that we have the following. We have two functions, let's say f from D to R, which we really don't need, but for the sake of being precise, let me take D to be a subset of R2, and f to be a function from D to R, and as I have said before, x0 y0 is a point in R2 which is a limit point of D. So suppose that the limit of f as xy tends to x0 y0 exists and is equal to this quantity LF, and suppose also that the limit of g as xy tends to x0 y0 exists, and this is given by LG. So then what happens? Then if I want to take the limit of f plus g as xy tends to x0 y0, it becomes the sum of these two limits. Similar thing happens for f minus g, product of fg. So if I want to consider the limit of fg as xy goes to x0 y0, then the limit will turn out to be equal to LF times LG. Also, if LG is not equal to 0, then limit of fxy divided by gxy will be equal to LF by LG as xy goes to x0 y0. Now somewhat more interesting things, if fxy is less than or equal to gxy in some open neighborhood of x0 y0, then LF is always less than or equal to LG. Note that when we are talking about these limits, we do not really need to take into account what happens with f and g at points which are far away from the points where we are considering the limits at. So if it so happens that if xy is less than or equal to gxy at all points which are near to the point that we are considering, then we will see that the limit of f as xy goes to x0 y0 is less than or equal to limit of g as xy goes to x0 y0. Now there is a sandwich theorem, which something you have seen before for functions in one variables. So again, if it so happens that for all points which is near to x0 y0, this inequality is satisfied that f of xy is less than or equal to g of xy, and this is less than or equal to h of xy. And also if this 2 has the same limit as xy goes to x0 y0, and if we call this common limit to be equal to L, then G must also have the same limit as xy goes to x0 y0. So this explains a lot of things about limit. So let us go forward to the epsilon delta definition, which we like so much in calculus. So suppose that D is a subset of R2 and f is a function from D to R, and in order to define limit, I would always need x0 y0 to be a limit point of D. And suppose that L is a real number, we say that the limit of limit of fxy as xy goes to x0 y0 is equal to L if and only if for every epsilon greater than 0 where exists a delta greater than 0, such that f of xy minus L modulus of this is less than epsilon whenever xy norm of xy minus x0 y0 is less than delta. Again note that this quantity is a quantity in R2, so we cannot apply modulus, we have to take norm in R2, and this quantity is a real number, so here we have to take modulus. And what does this condition boil down to? So we need that modulus of norm of xy minus x0 y0 must be strictly bigger than 0. So that means that xy cannot be equal to x0 y0 as we have seen in most cases in my previous slides, and this has to be less than delta. So this means that there should exist a open disk around x0 y0, and we are not considering the point x0 y0. So xy must belong to this open disk around it, and it is not equal to x0 y0. So if I want to explain this in terms of pictures, again what do I do? So suppose that this is our point f of so this point is given by x0 y0, and suppose that this is L. So I say that limit of f of xy as xy goes to x0 y0 is equal to this number if and only if the following is true. So again you give me an epsilon which is bigger than 0. I will construct this open interval L minus epsilon to L plus epsilon, and I will give you a delta which is bigger than 0. So you give me this epsilon, I will give you a delta such that what we call a punctured open neighborhood. So this is exactly this thing. If I call this b prime, so I'll give you a b prime such that the image of this b prime is contained inside this interval. So this is all what epsilon delta definitions are. So again I finish this this slide by working out a couple of examples. So let me work out the following example. So suppose f of xy is a function which is given by x square y divided by x square plus y square. So again, as always, our question is, so it is always very easy to check that the limit will exist if you take any point x0 y0 which is not the origin, because this is a bivariate rational function. And now I have given you a condition for a relationship between limits and continuity. So using that, you can see that this function is continuous, and as such this will imply that the limit will exist at all points x0 y0 which is not equal to the origin. So all we need to check in order to determine at what points this limit exists, all we need to check is at this point 0 0. So So the question is, does the limit of x square y divided by x square plus y square exist as xy equals to 0, 0? Okay, so note that this function was defined in R2 minus 0, 0, and you can see that if you take any neighborhood, you can take any neighborhood of 0, 0, which is contained inside R2. This will contain point of R2 minus 0, 0, of course, which is not equal to 0, 0. So what I want to say is that 0, 0 is a limit point of this set. If I call this D, then 0, 0 is a limit point of D. So asking whether the limit exists at 0, 0 makes sense. So now we have seen this kind of calculations before. We have in particular dealt with these functions before when we talked about continuity. So modulus of f of xy turns out to be less than mod of x, and you can easily check that modulus of x is less than or equal to norm of xy for every xy in R2. So what is a very short proof of this inequality? So what is this quantity norm of xy? Recall that this is just given by under root x square plus y square, and this is bigger than or equal to under root x square because y square is always bigger than or equal to 0. And what is under root x square? Here we are always going to take the positive square root or non-negative square root. This is going to be modulus of x. So we have proved this inequality. We have shown that modulus of xy is less than or equal to norm of xy. Now we apply our epsilon delta definition. So you give me any epsilon, I will take delta to be the same epsilon. So if norm of xy is less than epsilon, and which is delta also, then you can see that modulus of fxy is less than epsilon. So what does it prove? That limit of fxy as xy tends to 0, 0 exists, and not only that, it is equal to 0. I finish this very small calculation by taking f of xy to be the function y times sine of x 1 by x square plus y square if xy is not equal to 0, 0. So the question again is whether limit xy tending to 0, 0 f of xy exists. So does it exist? And if it exists, what is this? So note that this function is only defined again in R2 minus 0, 0 because at this point the denominator will vanish and you cannot compute this. So this is RD, and as we have seen before that 0, 0 is indeed a limit point of D. So it makes sense to ask if the limit exists as xy goes to 0, 0. Now the proof or the answer, solution, whatever you want to say, is very easy. So all we need to use is the fact that sine x or sine z or sine whatever sine z is always less than or equal to 1. So I start with modulus of f of xy. So I simply write it as modulus of y times modulus of sine of 1 by x square plus y square. As I said, this is always less than or equal to 1. So this whole thing is less than or equal to modulus of y. Now this guy is a non-negative quantity. So we can now use sandwich theorem if you want. So as xy goes to 0, 0, this function modulus of y goes to 0, and this function of course goes to 0, then this modulus of f of xy must go to 0. On the other hand, if you wished, you could have also used the epsilon delta definition. So again, if you give me an epsilon greater than 0, I would have chosen delta to be exactly the epsilon that you have given me, and you see that if modulus of y, okay, so first step is to relate it to norm of xy. So this is less than or equal to norm of xy. So you gave me an epsilon. I chose delta to be equal to epsilon, which is bigger than 0 by the defining conditions. And you see, if this is less than or equal to delta, which is epsilon in our case, then f of xy is less than epsilon. So what we have proved is that this limit exists, and not only that, this is equal to 0. So in the course of this, in the span of this last two videos, I have introduced you to the notions of limits and continuities of functions in two variables. In what follows, we are going to talk about partial derivatives, which is our first step to understanding the notion of differentiation for multivariable calculus.